Hello, this tutorial is on some basic technical and also pathophysiological aspects of cerebral microembolic signal detection. What is microembolic signal detection anyway? If we place an ultrasound transducer over the temporal bone, we can collect information on the blood flow velocity of the middle cerebral artery at a depth of 5 to 6 centimeters in the vast majority of human beings. Let's take a closer look how this is happening. On the left side we have the ultrasound transducer emitting ultrasound pulses. In this case, the ultrasound pulse has already reached a blood vessel, which is depicted on the right side. Let's assume that the erythrocytes flow from the lower right corner to the upper left corner. The lower half of the image illustrates the interaction between the incoming ultrasound, which is depicted by the short black arrows, and the erythrocytes. Since the wavelength of the ultrasound is 100 times longer than the size of the erythrocytes, the ultrasound is not just reflected, but scattered into all directions. Fortunately, part of this scattered ultrasound is directed towards the ultrasound transducer. The sum of all that ultrasound energy, which then can be received by the ultrasound transducer, is depicted by the large open arrow. If an embolus is entering the bloodstream for a short moment in time, the backscattered ultrasound energy is increased. The embolus is depicted here as a large red circle, the increased backscattered energy by the bold lines of the open arrow. The short-lasting intensity increase is both visible and audible. You can clearly see in the FFT spectrum the red dot, which is the signature of the embolus, and you can also hear it. Please click on the gray arrow on the upper left corner to listen to the signal. Here we can see two other examples of microembolic signals arising from microemboli. They are shown as short-lasting, high-intensity signals within the FFT spectrum. We can, however, also look at an embolus in the so-called time domain, and not only in the frequency domain, which is actually the FFT. On the x-axis we again have time, but the interval on the right side is much shorter than on the left side. Actually, the time interval on the right side is equal to the duration of the small yellow square in the figure on the left side. The biggest difference between the time domain and the frequency domain signal, however, is on the y-axis, whereas in the FFT, the y-axis gives the Doppler shift frequency or velocity. The y-axis in the time domain signal gives the intensity. Here we can see a typical microembolic signal in the time domain, starting at around 12 and ending at around 30. We can see a typical crescendo and decrescendo, and also a change in wavelength corresponding with a changing velocity during its time course. But above all, we can clearly see that the embolus signal has a much larger intensity than the background signal. But the background signal is not only much weaker than the embolus signal, it is also pretty unregular. We can both measure the maximal amplitude of the background signal, which is the small white bar, and the maximum amplitude of the embolus, which is the large white bar. In this case, the ratio is 1:17. With a little bit of wizardry, we can calculate that the embolus has an intensity of 24.6 dB when compared to the Doppler background. This is also called the embolus to blood ratio. One of the reasons why it makes sense to know the dB value of a microembolic signal is the reliability with which it can be detected. The results of this study showed that from 9 dB on, the inter-observer agreement was very high. In other words, if an embolus has an intensity of at least 9 dB, it is very likely that it will be detected by different observers. So, taken together, microembolic signal detection is quite accurate when compared to other established ancillary tests we use in daily practice. So, what makes microembolic signal detection so special? Here we can see a patient who is prepared for carotid surgery. We can see that EEG electrodes are already mounted, as well as a TCD transducer on the side of surgery. On the right side, we see a signal that will be recording during a preparation and just before clamping. Let's take a closer look to it. After the first cardiac cycle, we see a strong decrease of the blood flow velocity in the middle cerebral artery, lasting approximately 1 second. This is due to pulling the internal carotid artery and hence obstructing the blood flow through it. Because this patient had an insufficient intracranial collateralization, the flow in the ipsilateral middle cerebral artery almost vanishes. Then the surgeon releases the vessel, the flow in the middle cerebral artery restores, and precisely 1 heartbeat after releasing the vessel, there is an embolus, which is indicated by the red spot in the FFT spectrum. If we take the velocity of the microembolic signal into account and the distance between the middle cerebral artery, where we pick up the microembolic signal, and the internal carotid artery, where the surgeon had pulled the vessel, it is obvious that pulling the vessel and hence irritating the plug inside caused the release of this microembolus. In other words, the release of microemboli indicates an increased propensity of the plug to shed emboli. Microemboli detection by means of TCD is the only method to evaluate this plug property. By clicking on the gray arrow in the right upper corner, you can listen to the signal. First, you will hear the sudden decrease of the blood flow velocity, and soon thereafter the microembolic signal. This is another example of an embolus occurring after manipulating a plug. Please press again on the gray arrow to listen to the signal. Now let's look at some technical aspects, and the first will be, how can I hear a microembolic signal best? The first step in detecting a microembolic signal is hearing a signal intensity increase. It has been shown that this is best done in a silent environment, which of course can easily be created by wearing a set of good headphones. Since listening to a Doppler signal in search of microembolic signals can sometimes last very long, it makes sense to choose headphones that you can comfortably wear for 1 or even 2 hours. Another question that might arise is, can we deduct from the microembolic signal how large the embolus was and what it was made of? This graph shows the relationship between the insonation frequency on the x-axis, the backscatter on the y-axis, as well as 3 different kinds of material, which is fat, air and red cells, as well as 2 different sizes of each material. Let's focus on the frequency which is used by almost all TCD machines, 2 MHz. Additionally, we focus here just on the red blood cells. It is obvious that the larger the particle, the more ultrasound is backscattered. We can also see that there is a difference for the different materials, assuming that we have the same size of each material. Air scatters more ultrasound back than fat. Red blood cells scatter the least ultrasound back. This all might suggest that we indeed can reliably discriminate between different sizes and materials. The problem, however, arises when we don't know what the actual composition of an embolus might be. It is, for example, obvious that a tiny gas bubble of 20 micrometer size gives rise to approximately the same backscatter than a red cell clot of 200 micrometers. However, for very low or very high dB values, it is very likely that we look at either particulate or gaseous emboli. In this case, we have at least 6 microembolic signals in the Doppler spectrum. The first 5 ones are so intense that they distort the signal and are even visible beyond the FFT. It is hardly conceivable that such strong microembolic signals are caused by particulate emboli. You can listen to the signal by pressing on the gray arrow in the right upper corner. In this study, it could be shown that gaseous emboli have a higher intensity on average, but also that extremely high intensities only occur with gaseous emboli, as well as extremely low intensities only with particulate emboli. This is most obvious in the lower figure, where the intensity of the embolus is expressed as effective sample volume length. Since it is very important not to miss an embolus, especially when the incidence is very low, I will shortly discuss 2 adjustments on the TCD machine. The embolus to blood ratio, or the intensity of an embolus as compared to the Doppler background, is determined by several factors, among other things the sample volume length. The sample volume length is in this formula given by the capital letter L. It's in the denominator of the formula, which means that a large sample volume length will decrease the embolus to blood ratio. So it is preferable to use a rather short sample volume length. Normally 5 mm will be optimal. In this example, the gain is adjusted as we usually would do for the estimation of blood flow velocities. You already can see some red spots, possibly being microembolic signals. If we decrease the gain considerably, the microembolic signals are much better visible. So it makes sense to set the gain to the rather low values. You can listen to the signal by pressing the gray arrow in the upper right corner. Another important technical topic is the question whether a given automated microembolic signal detection system is working or not. This is an example of a microembolus signal detection system that runs on an external laptop and can be hooked up to almost any TCD machine. You can see the microembolic signal in the upper blue trace. The red signal below shows how the detection algorithm deals with this signal. It has been reported in the literature that the agreement between this algorithm and the human observer was pretty high. The problem, however, is that these data were published by the same people who invented the system. There is hardly any paper where a given algorithm was evaluated independently or in comparison to other algorithms. This rather old publication showed rather low accuracies. So, if you want to use the automatic embolus detection software that might be implemented in your TCD system, please test it yourself under the circumstances you want to use the TCD machine for. Only that will determine whether you can use it in daily practice or not. Another question that often arises is, how long do we have to measure? The time we need to measure heavily depends on the incidence of microembolic signals. Very often this incidence can be pretty low. To make things even worse, the distribution of microembolic signals in time is not even. In this publication, several patients were monitored for 8 hours, and you can see in patients number 6, 4 and 8 that not only the incidence differs considerably, but also the occurrence of microembolic signal in time. A lot of data that have been published on microembolic signals rely on a 1-hour recording. But you can easily see, for example, in patient number 4 that we have negative and positive hours. These 3 patients are, by the way, all patients with a symptomatic carotid artery stenosis. And the measurement took place in the ipsilateral middle cerebral artery. One solution for this problem might be a long-term recording by an ambulatory device. We can see here a volunteer wearing the system. The transducer is attached to a set of glasses. On the other side of the glasses there is a counterweight The whole system can be easily worn by the patient in a small pouch. On the right side, we see another volunteer wearing a typical setup for the analysis of an obstructive sleep apnea syndrome. And at least to me, the social acceptability of the TCD system might be even higher than the one of the obstructive sleep apnea syndrome setup. Here we can see the inventor of the TCD, Rooney Arslit, on the left side. He is actually wearing the system you just saw under the headband. On the right side, you can see the Doppler signal that is recorded. In the first part of this short movie, he is talking to his wife, and soon thereafter he is playing tennis. You then can see easily the hemodynamic changes in the Doppler signal. The purpose of this movie is to illustrate that it is really possible to measure the TCD signal with an ambulatory device even while considerably moving around. When you advance to the next slide, the movie will start automatically.
Ja?
Okay.
This system also sports an automatic embolus detection system. You can see here an example of an embolus that has been detected successfully. We have been testing this software in a patient group with symptomatic carotid artery stenosis with a degree of stenosis between 30 and 70%. And we indeed found a very, very low incidence of microembolic signals. 2 human observers analyzed 20 hours of TCD signals. Both detected only 4 microembolic signals. The automated detection system also detected these 4 microembolic signals plus an additional 23 false positives. This is a typical situation because it is very important that all true microembolic signals are detected. This will very often go at the expense of a rather low specificity. In other words, the system will detect false positive signals. The system, however, offers the possibility to manually evaluate all possible microembolic signals according to the automatic detection system. The possible microembolic signal is then embedded in short segments of Doppler signal, which means that a human reanalysis of these segments can be done within a short time. So let's now wrap up what the take-home messages of this tutorial are. If a relatively large particle passes through the sample volume of the TCD in the middle cerebral artery, it will give rise to a microembolic signal. The microembolic signal can be looked at in the frequency and in the time domain. The intensity of the microembolic signal is measured in decibels or dB. The first step in identifying a microembolic signal is hearing a signal intensity increase. This can best be done by wearing good headphones. Despite the fact that a relatively large embolus will scatter back more ultrasound energy than a relatively small embolus, and that different materials will also differ in their backscatter properties, it is not easy to determine the size and the composition of the embolus that gave rise to the microembolic signal. One can only be sure that rather small intensity microembolic signals stem from particulate emboli and rather large microembolic signals from gaseous emboli. It is best to use a sample volume length of 5 mm and a rather low gain for microembolus signal detection. If you want an automatic system for microembolus detection, you should first test it under the circumstances you want to use it for. If the incidence of microembolic signals in the patient group you want to examine is rather low, you might consider using long-term recording systems. Thank you for paying attention to this tutorial. I hope you liked it. If you want to react or have a question, you will find my email address on the very first slide.